Dear students, today I would like to discuss molecular orbital diagram of octahedral complexes. Myself Dr. Digna Varghese. Molecular orbital theory and composition ligand group orbitals. Molecular orbital theory, which is also known as adjusted crystal field theory or ligand field theory. The covalent bonding complexes may be considered in terms of molecular orbital theory. Molecular orbital theory suggests that there will be overlap between metal and ligand orbitals and forms molecular orbitals. This can be done systematically by using some principles of group theory. Ligand field theory is actually the application of molecular orbital theory. Ligand field theory describes the bonding, orbital arrangement, and other characteristics of coordination complexes. The valence orbitals on the metal and the ligand are used to form salcs. Salc means the symmetry adapted linear combinations. That is actually obtained from the character table. We are discussing here the octahedral complexes. And we have to draw the molecular orbital diagram for the octahedral complexes. So this is the character table for the OH point group that you have already studied in group theory. Sigma bonding ligand has a single valence orbital directed towards the central metal atom. Sigma bonds to all 6 ligands in octahedral geometry. The metal forms sigma bonds to all 6 ligands in octahedral geometry. The molecular orbitals formed by coordination results from the donation of 2 electrons by each of the 6 donor ligands to the d orbitals on the metal ion. In the case of metal ion, there is the valence orbitals like Eg orbitals that can form sigma bonds with the ligand orbitals. Each ligand can donate 2 electrons to the metal. In octahedral complexes, the ligands approach along the x, y and z axis. So there is sigma symmetry. Orbitals form bonding and anti-bonding combinations with the dz square and dx square y square orbitals. We know in octahedral complexes, ligand approaching the metal ion through the x, y and z axis that we have already seen our previous classes. The dxz, dyz and dxy orbitals remain non-bonding orbitals in sigma bonding octahedral complexes. That means these orbitals are not involved in bonding. Some weak bonding or anti-bonding interactions with the s and p orbitals of the metal ion can occur to make a total 6 bonding and 6 anti-bonding molecular orbitals. The 6 ligand orbitals collectively form a reducible representation in the point group OH. The 6 ligand sigma orbitals, that is sp or s plus p hybrid orbitals with the same symmetry that can match the symmetries of the 4s, 4px, 4py, 4pz, 3d z square and 3d x square y square metal orbitals. The combination of the ligand and metal orbitals to form 6 bonding and 6 anti-bonding orbitals with A1g, Eg and T2g symmetries. The 6 bonding orbitals are filled by electrons donated by the ligands. The metal T2G orbitals do not have appropriate symmetry to interact with the ligands and are non-bonding. T2G orbitals means the dxy, dxz and dyz orbitals that acts as non-bonding in sigma bonding octahedral complexes. In molecular symmetry terms, the 6 lone pairs from the ligands, one from each ligand, one lone pair from each ligand, form 6 symmetry adapted linear combinations of orbitals, also sometimes called ligand group orbitals. In molecular symmetry terms, the 6 lone pair orbitals from the ligands form 6 symmetry adapted linear combinations of orbitals, that is also known as ligand group orbitals, that can overlap with the metal orbitals to form sigma bonding in octahedral complexes. The irreducible representation that these span are A1G, T1U and EG. That is actually the 6 ligand group orbitals, that is A1G 1, T1U 3 and EG 2. Total 6 ligand group orbitals, each contain 6 lone pairs, lone pair, that means total 12 electrons, which is donated to the metal orbitals. These are actually the reducible representation that we can obtain from the character table. We have to identify the irreducible representation for the complex octahedral symmetry. Then the irreducible representation is given as A1G, EG, T1U, that is actually the symmetries of the ligand group orbitals, that is obtained from the character table of the point group OH, and the reducible representation can be calculated by using the formula n is equal to 1 by h sigma x chi rx into chi I x into n raised to x. From this equation we have to calculate by the use of a character table, and we get the ligand group orbitals as A1G, EG and T1U for an octahedral Ml6 complex. The characters of the reducible representation are derived by counting the number of vectors that remain unmoved under each symmetry operation of the OH point group. The reducible components of lambda sigma are obtained by the application of this equation. The A1G group orbitals have the same symmetry as an s orbital on the central metal. We know the metal atom has 9 valence orbitals, that is n-1 d orbital, ns orbital and np orbitals. So the metal atom has 9 valence orbitals that span these irreducible representations. The s orbital is labeled as A1G, a set of 3 p orbital are labeled T1U, and the dz square and dx square y square orbital is labeled as EG. The molecular orbitals we shall using here will be of the LCAO type, that is linear combination of atomic orbitals. Constructing the linear combinations of the ligand orbitals, that is ligand group orbitals, that we have already seen for the SALC, that will overlap with the metal orbitals along the octahedral bonding axis. There are two theories to explain the bonding in complexes. One is crystal field theory that we have already studied. According to crystal field theory, there is some electrostatic interaction between the metal and the ligands, that the bonding between the metal and the ligand involves the ionic bonding. But there are some effects. We know nephelauxetic effect, that is actually electrons are shared between the ligands and the central metal ion, comes from the nephelauxetic effect. That is the additional evidence for the evidence for the covalent bonding existing between the metal and the ligand orbitals, and there is some additional evidence for the covalency is obtained from the metal ligand bonds is provided by the electron paramagnetic resonance, that is EPR. Actually, the complete bonding can be explained only by the molecular orbital theory. We know for simple molecules, the molecular orbitals are formed by the linear combination of the atomic orbitals. That is, consider an atom X having a molecular orbital like this and Y having molecular orbital like this, and these are overlaps to each other to form a molecular orbital XY, and there is number of atomic orbitals combined to give the same number of molecular orbitals. Here two molecular orbitals are formed by the combination of the two atomic orbitals. One is bonding molecular orbital and the other one is anti-bonding molecular orbitals. Bonding molecular orbitals have lower in energy and anti-bonding molecular have higher in energy. If the electrons in X contains one electron for sharing and Y containing one electron for sharing, the atomic orbitals are combined to give the molecular orbitals having two electrons, and that will occupy at the lowest energy state, that is bonding molecular orbitals. If the electrons are more closer towards the X atom, it means X is more electron denser than Y atom. That's why in a covalent bond, X occurs a partial negative charge and Y occurs a partial positive charge due to this. If the electrons are present more closer to the Y atom, then Y get the negative charge and X get the positive charge. So that will explain the polarity between the atoms. If the energy gap between the molecular orbitals is very higher, that means it is completely becomes ionic bonding. Okay. So in molecular orbital theory, the metal ligand interaction is somewhat covalent interaction, that the additional evidences are provided by electron paramagnetic resonance. The metal orbital must be capable of positive overlap with a ligand group orbital directed along the bonding axis. In order to actually participate in a sigma bond, we are now considering only the sigma bond effect in an octahedral complex. Okay, but sigma bond within the complex means a metal orbital, say s orbital, must be capable of a positive overlap with the ligand orbitals in a positive overlap with the ligand group orbital directed along the bonding axis. The bonding axis is necessary, that is x, y, z. So according to molecular orbital theory, the metal ligand sigma bonding in octahedral complexes results from the overlap of suitable atomic orbitals of the central metallic cation with the ligand sigma orbitals. In order to actually participate in a sigma bond within the complex, a metal orbital must be capable of positive overlap with a ligand group orbital directed along the bonding axis. The formation of 6 metal ligand sigma bonds in an octahedral complex takes place through the following steps. First step is the central metal cation of 3D series elements contains all the 9 valence shell atomic orbitals. That is, we have already discussed, that is 4s, 4px, 4py, 4pz, 3dxy, 3dxz, 3dyz, 3dx square y square and 3dz square. 1 s orbital and 3 p orbitals and 5 d orbitals. Together we get 9 valence orbitals. All the 9 orbitals have been grouped into 4 symmetry cases. That is, one is 4s. Their symmetry properties in an octahedral complex can be determined by reference to an octahedral character table that reveals that the s orbital transforms as A1G and the set of p orbitals that transforms as T1U, whereas the 5 d orbitals lose their degeneracy to form 2 sets, that is dxy, dxz, dyz transforms as T2G and dx square y square dz square transforms as EG sets. In an octahedral complex, there is 6 ligands are approaching along the axis. According to Christopher theory, in an octahedral splitting, the ligands are approaching along the axis. The ligands are on the z-axis, ligands are approaching to the metal through y-axis, ligands are approaching to the metal through x-axis. So, the 6 ligands are approaching along the axis, in which the sigma orbitals along the plus x, minus x, plus y, minus y, plus z and minus z axes have been represented as, we can represent the sigma bonds along the axis as sigma x, sigma minus x, sigma y, sigma minus y, sigma z, sigma minus z. Okay. Determining the symmetries of the orbitals that will participate in the bonding does not tell us what specific combinations of ligand lone pair orbitals should be used in constructing the 6 ligand group orbitals. The sign of the wave functions for the metal A1G orbital is everywhere the same, which is taken to be positive. The 6 ligands interact equally with this orbital and orbital must have a positive sign. In this case, the A1G symmetry, the sign of the wave function for the metal A1G orbital is everywhere positive. We know s orbital is spherically symmetrical, so the sign must be positive everywhere. The 6 ligand interact equally with the orbital and the orbital must have a positive sign. The overlapping means positive overlapping. Okay, that is the most proper way of overlapping and forming metal ligand sigma bonds. In order to actually participate in a sigma bond within the complex, a metal orbital must be capable of positive overlap with a ligand group orbital directed along the bonding axis. The A1G metal orbital will be spherically symmetrical and positive sign everywhere, and it can overlap with the ligand group orbitals on all axes. That means the sign of the wave function for the metal A1G orbital is everywhere the same, which is taken to be the positive. The 6 ligands can approach and or interact equally with this orbital, and each contributing orbital must have a positive sign. Okay, in this case we can see the sigma x direction and y direction, z direction here, and we can draw the y direction also, and we can represent as sigma bond along y-axis and sigma bond along minus y direction. Okay, and the bonding for the ligand orbital, the positive sign should be like this towards the metal A1G orbitals and negative. So there is a positive overlap occur, and here also positive sign. We are considering the negative and sigma y here, sigma x here, sigma z here, that is the bonding along the positive side of the axis. Okay, and sigma minus x, sigma minus y and sigma minus z means bonding overlap is positive but along the minus axis side. So that is can be represented as sigma minus x, sigma minus y, sigma minus z. So the 6 thus the A1G LGO can be, ligand group orbital can be constructed from an additive combination of the 6 ligand orbitals. That is 6 ligand orbitals means sigma x, sigma minus x, sigma y, sigma minus y, sigma z and sigma minus z, and we get like this: sigma A1G is equal to 1 by root 6 sigma x plus sigma minus x plus sigma y plus sigma minus y, sigma z plus sigma minus z. Here the sigma and capital sigma and small sigma represents the wave functions for the ligand group orbitals and ligand orbitals. That means sigma corresponding to the wave functions of the ligand group orbitals, and here the small sigma corresponding to the wave function of the contributing ligand orbital. And 1 by root 6 is the normalization constant. We can also this get from the SALC, symmetry adapted linear combination of the SALC, that is the LGOs can be constructed for the sigma bonds of an octahedral complex. Here we are showing only the A1G system. Likewise, the T1U and EG symmetries. The same conclusion could have been reached in a more formal manner by considering the 6 sigma bonds of an octahedral complex as vectors. Okay, and determining how they transform under the symmetry operations of the octahedral point group, and we get the reducible representation that results from the counting the number of vectors that remain unchanged by each symmetry operations, and yields A1G, EG and T1U as its irreducible components, indicating that these are the symmetries of the metal and ligand group orbitals that will be suitable for forming sigma molecular orbitals in the complex. In the same conclusion reached earlier by considering the capability of the metals, valence orbitals and the ligand orbitals for overlapping. Okay, and we have to know the 1 by root 6 is the normalization constant, and we know psi is equal to C151 C plus C252 as the general formula, and the normalization constant can be calculated as C1 square plus C2 square should be equal to 1, In this case, 1 square plus 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 1 square is equal to 6. So it is not equal to 1. So we have to normalize these orbitals. And the normalization constant can be get by 1 by root of c1 square plus c2 square. So we have to give like this 1 by root 6. By this we are normalizing these ligand group orbitals for proper overlapping. In this case, this is shown for the dx square y square orbitals, that is the d orbital along the axis x and y axis, and this is the T2G set corresponding to the dxy orbitals and in between the x and y axis. Okay, the T2G set however will have the lobes directed between the bonding axis, say x and y, and thus will yield no net overlap with the ligand orbitals, because ligand is approaching towards the metal through bonding axis, but the T2G, one of the T2G orbital is shown as example for the common procedure for the T2G set, that the dxy is approaching to the ligand is in between the bonding axis, so there is no direct contact between the metal and the ligand orbitals, so there is no overlap occurs. So the T2G set will have the lobes directed between the bonding axis and thus will yield no net overlap with the ligand orbitals. And in this case, dx square y square orbitals, an appropriate choice of sign, that means the negative negative, positive positive, negative negative, positive positive, then only there provides the positive overlap with the dx square y square orbital occurs. So these dx square y square orbitals actually the same direction as that of the ligand orbital, so there is positive overlap occurs, so there is sigma bonding occurs, but in the case of dxy there is no positive overlap, so there is no sigma bonding for T2G set. The A1G LGO can be constructed from an additive combination of the 6 ligand orbitals, that is sigma A1G 1 by root 6 sigma x plus sigma minus x plus sigma y plus sigma minus y plus sigma z plus sigma minus z. In this, sigma and sigma are represents the wave functions for the ligand group orbitals and the wave functions for the contributing ligand orbitals, and 1 by root 6 is the normalization constant. For A1G, 1 by root 6 is the normalization constant, and likewise for p orbital, d orbital. For p orbital and d orbital, there is some other normalization values that we can see from the table, as how A1G 1 by root 6 and p labeled as T1U, that is 1 by root 2, and d is a square EG 1 by root 12 and dx square y square EG 1 by root 4. So the LGO can interact with the dx square y square orbital will be represented as follows: sigma x square y square, that is 1 by root 4 is the normalization constant, that can be written as 1 by 2, sigma x plus sigma minus x minus sigma y minus sigma minus y. Okay. The LGOs that matches the dz square metal orbital is sigma z square 1 by root 12 2 sigma z plus 2 sigma minus z minus sigma x minus sigma minus x minus sigma y minus sigma minus y. That can be, to find the ligand sigma orbital combination for the dz square orbital is poses some difficulty. The analytical function for the 3D square orbital is proportional to 3z square minus r square. The proper orbital combination is easily written down by substituting r square is equal to x square plus y square plus z square. Therefore, 3z square minus x square plus y square plus z square is equal to 2z square minus x square minus y square. Consequently, the proper combination for 3D z square orbital is 2 sigma z plus z sigma z minus z minus sigma x plus sigma minus x minus sigma y minus sigma minus y is equal to 2 sigma z plus 2 sigma minus z minus sigma x minus sigma minus x minus sigma y minus sigma minus y. These are obtained by the character table, and also the sigma z square is equal to, therefore the LGO that matches the dz square orbital is 1 by 2 root 3 or 1 by root 12 2 sigma z plus 2 sigma minus z minus sigma x minus sigma minus x minus sigma y minus sigma minus y. Okay. Likewise, the 3 LGOs of T1U symmetry that will overlap with the metal orbital p orbitals, metal orbital p orbitals are constructed in a similar manner as shown in A1G, dx square y square and tz square. Therefore, we can get the LGO of corresponding to x px orbital, that is sigma x is equal to 1 by root 12 root 2 sigma x minus sigma minus x, sigma y is equal to 1 by root 2 sigma y minus sigma minus y, sigma z is equal to 1 by root 2 sigma z minus sigma minus z. Since the metal T2G orbitals cannot participate in sigma bonding or overlap, they are considered as non-bonding molecular orbitals in complex. Here the molecular orbital energy diagram for the sigma bonds in an octahedral complex. For example, CONH363 plus ion. In this CO group has 6 electrons in its cobalt 3 ion has 6 electrons and D6 configuration, and from the ligands it get 2 into 6 12 electrons, therefore total 18 electrons. Okay, ligand donates this, electrons can be arranged in like this: 2 electrons for A1G and 6 electrons for T1U and 4 electrons in EG, 2 6 8 plus 4 12, then 6 electrons in T2G level. Okay, total 18 electrons. So the molecular orbital configuration is A1G2, T1U6 and EG4 and T2G6. Therefore, in the complex, hexamine cobalt 3 ion is diamagnetic because there is no unpaired electrons. And the energy difference between the T2G to EG star level is small. In the case of COF6 3 minus, if in this case CONH3 3 plus, it has a higher delta value, so pairing occurs. But in the case of COF6 3 minus, the electrons can move from this level to this level, so that must be paramagnetic also or high spin complex. In this case it is a low spin complex. Okay, so it's a diamagnetic complex, and we can draw the molecular orbital energy diagram for an octahedral complex. Thank you for your interest and attention.